again to this afternoon's talk. Today we have a talk by one of our ex-students, professional geologist, Leong Thye. And the topic is on the screen now. Innovative approach in risk and stability assessment of an engineered rock slope. So I understand from him this is actually a case study, actual project. So before he proceeds, let me quickly go through his CV. Actually, he sent me a very long CV, a very long one, so I don't have time to read it. I will just pick up the gist. Okay, he graduated with a BSc honors from UKM, 1986. That's many years ago. So that's 37 years ago. So his working experience since graduation, 37 years. And he's currently a senior manager in this Minconsult. It's a geotechnical consulting firm. He has actually worked in many companies since he graduated. For example, he was in Hill, he was in Web Structures, Syndrome Berhad, Geopancha, Road Builder, etc. So it's quite a long list of companies that Koay has worked in. And he has been involved in many projects, numerous projects. Going through his CV, he was involved in dams, a wide variety of projects, dams, tunnels, slopes, railways, highways, piling, ground improvement, high-rise, civil works, water treatment plants, airports, etc. It's a very wide spectrum of engineering projects. And he has also worked overseas in say Bangladesh, Vietnam. Yeah. So he worked, this is what surprised me a bit. He worked in the capacity of as an engineering geologist, mostly an engineering geologist, but also sometimes as a geotechnical engineer. And so that, to me, that is quite interesting. Maybe we will discuss that during the Q&A. Okay. Okay, in terms of publication, not many. I guess he was too busy involved with the project, so he didn't have time to sit down and write papers. But maybe we will encourage him to sit down from now on, write up some of the projects. Yeah. So we can publish some in our journals, for example. Okay, with that very brief introduction. Actually, his CV is very long. Yeah, but very long list. Okay, with that, I give the floor to the speaker, Mr. Koay. The floor is yours. Okay.
Thank you, Mr. Tan, for your introduction. I'm really honored to be presenting to the audience, mostly I suppose geologists and maybe some other professionals. Good afternoon, ladies and gentlemen. Okay, the topic from my topic today is actually an innovative approach in risk and stability assessment of an engineered slope, rock slope. Basically, this was a project which I have done some time back, maybe more than almost 15 years ago. So, but it was presented in a slope conference in Bali in year 2019. So today I want to share with you my presentations. Most of my presentations which I did in 2019. Okay, next slide. Okay, for rock slope, we are always being faced with a situation whereby we have, say for example, this big slope that you have, and we are asked to assess the stability of this type of slopes. And these type of slopes, they have a lot of configuration, a lot of geometry, a lot of berms, a lot of the size of it. So with one eye, you cannot say the slope is bad, unstable, and all that. We as engineering geologists, we have to identify to our client where exactly is the problematic area, where to carry out repair work, where are the mitigation. So we have to come up with an idea how to actually map this the entire slopes. So this one is you know, I think this is a very famous rock slope in North South Highway and you can see the scale of it. You will find a problem with one slope. You cannot declare that, oh, the entire slope is problematic So we have to pinpoint where exactly are the high risk slopes, the moderate risk slopes, and the low risk slopes So we have to come up with an idea how to do it So what we did was to introduce the concept of mapping cells mapping zones The next slide will show you Okay, this you can see is a typical slope that we have. So we have to subdivide these slopes into cells. So I call it mapping cells so that we will actually study piece by piece each mapping cells, and then we start to give rating. Rating in terms of stability, the stability being the likelihood of slope failure, and then what are the consequences? The consequences that's particular for that particular zone. So particular mapping cell. So I have actually for my project, I actually subdivide into about 20-meter width. Each of them separated by the berms. What you can see is the yellow line is actually the chainage point, chainage line. The yellow line vertically down is the chainage line. The horizontal line is actually coincide with the berm, the actual berm, the red line. Red lines coincide with the berm. So this way we are able to get a graphic representation of the entire slopes with the assemblage of all these cells, all these mapping cells. Next, I think, okay. So as I mentioned earlier, first you need to subdivide the slopes into discrete mapping cells. This is to give you the graphic representation of the entire slope. This is also to make it more manageable. We can map it in a more manageable area. The 20-meter width was actually selected because it was conveniently within one shot of a camera view angle. And for each cells that I mentioned earlier, it is assessed for 5 instability factors and 3 consequent factors. I'll explain later in what is instability factors and consequent factors. Then we'll aggregate the scores to develop the consequent scores, the instability and consequent scores. Then subsequently, these scores will be graphically represented in a profile format to develop the risk profile. And this profile will actually reflect the actual shape of the slope or the whole slope. Thereby, this one, once we have done this, we can able to highlight where are the high risk area, where are the moderate risk area, and also the low risk areas. I'll go with the next one. Okay, what are the tools and methodology we did now? We have actually airborne LiDAR survey. So in those days, we were one of the earlier user of airborne LiDAR survey. Then we have a topo map and cross sections generated from the LiDAR. We carry out we take a lot of base photographs for each mapping cells. We did the geological mapping of discontinuities. Then we have field identification of unstable rock mass, carry out zero plots, and also kinematic analysis of unstable blocks. We also gather from our cross sections and topo the slope geometry of the entire slopes. Then we develop the instability and consequence profile, and finally the resulting profile is the risk profile, which will be seen as for the entire slope. Next we have Okay, the field works. Field works, we started by, at the site, we started by marking the changes on the rock face at every 20 meter. The reason being we want to capture the change marking on our base photographs also. So second, we photograph the slope face, ensuring that the change markings are captured in our photographs. We carry out the geological mapping of the rock slope for discontinuities, looking for faults and all that. On top of that, we have close inspections by foot. That means we walk along the berms, looking at all these, try to map the entire rock face, the bench face. And in those inaccessible areas, we have to use skylift crane. And we also, while mapping, we identify potential unstable blocks, rock masses. And any other slope features, like whether we have shotcrete, we have proper berms and drains, etc. Next, okay, this is an example of how we develop our base photographs. Can you see my cursor? Anybody can see my cursor?
Yes, yes.
I can
Yes,
see the
can see.
cursor. Okay, you see in this one, the cursor is shown at change 140, and it's visibly marked on the rock surface also. 140 here is 160, so it's physically marked on the rock surface. So this is actually like one cell, one mapping cell. This is also another mapping cell. This is also another mapping cell, and so on and so forth. And in this base photograph, we actually map the joints, and we label in our base photographs. Say 022. This is in deep direction. 022 deep direction with deep angle of 20. All these are in deep direction and deep inclination. Then we also demarcate phase. For example, this is P12, P20. This is a potential unstable block which we want to study later on by kinematic analysis and serial plots. So you can see that some of these, all the features that we can capture on the field are being put onto these photographs. So, okay, next we will go through, okay, these are the discontinuity mapping done at the bench face. Also, we have a bit of rope access inspection. Okay, that time we have this is a geologist from Italy, lady, and she got license to actually do this rope access. So she did a tryout over at the site. We have foot inspection by foot. We walk along the berms, and in this case, we notice a rock fall over here. And we also take note of the width of the berm. We measured the width of the berm. But actually, the width of a berm was measured through AutoCAD drawing from the cross section that was developed from LiDAR, and we have the skylift crane to inspect those slopes that are inaccessible. So we have a lot of equipment actually. Okay. Next. Okay, this is our LiDAR scanning, the terrestrial LiDAR scanner. It was from the Italian that who did this job with us. And the LiDAR scanner is only able to give us the slope profile, cross-sectional profile. But unfortunately, at the bottom here, we are not able to get the width of the rock ditch lah. So as you can see, the bottom photo is a measurement of the rock ditch. So this is being supplemented, the cross section has been supplemented by actual field measurement of from the rock face to the, in this case, the guardrail lah. Okay, okay, as I mentioned earlier, we have the LiDAR survey, which generated the contours. We have the aerial photographs. These are being superimposed on our aerial photograph with the contours. So these are all generated from the LiDAR. What are the causes of rock slope instability? So basically, we have in this presentation, I'm referring as instability factors, which are influencing the stability of rock mass and influencing the probability of a rock fall. Firstly, we have the steepness of slope or the bench face. The steeper the slope or the bench face, the more unstable is the stability. Secondly, we have the geologic structure, whether whether it's weak or highly weathered or highly jointed rock mass, it's always more unstable. Thirdly, we also look at the joint condition, whether there is clay infill, whether it's wet or persistent joints. These are all features of more unstable condition. Fourthly, we perform the kinematic analysis when we detect the interaction of joint orientations, looking out for plane wedge or toppling failures. We also look at within that that particular mapping cells whether we have any other kinematic analysis failure or not. So if it's more than one, whether it's 0 or 1 or more than 1, we will highlight it. So we'll give certain scores to it. So okay, this is a typical kinematic analysis. We're looking at the kinematic feasibility. It's plotted in a stereo plot. This was by Rockpack. This Rockpack is a very simple stereo plots. Okay, for example, here in this example, you can see there are 3 joints. Basically, J1 is this one. This is the great circle of the face, and is represented by this dip vector, which is this point. So J1 is 040 DD dip direction and dip angle of 50. We have J2 here. J2 is this blue one, with this represented by great circle, and the dip vector is here. And J3 is the green one, okay, which is here. So from this analysis, we carry out this analysis using dip vector, because it's very easy to find out, just like looking at the representative dip vector. And for example, here we are carrying out the Markland test. The Markland test is actually represented by this crescent. This crescent. On top of that, we further demarcate by plus minus 30 degree to have more unstable condition, whereby this cone represented between plus minus 30 degree is more critical. If any of these, like for example, this J1, the dip vector is falling within this cone, then this is more unstable, more likely to fail under this condition. And in this case, for example, you can see a bit of, here is a toppling failure happening in this triangle, which is here. You see the toppling failure is likely to occur here. And yeah, and J2 is relatively safe lah. It's outside the Markland critical crescent lah. So okay, then this is an example of the kinematic analysis being carried out. This one, we plot the entire slope also, all the points, just to look at the trends of the joint systems. So over here we can see a couple of what do you call, a couple of trends shown by this like a fault plane, a basal plane here, then some shear planes here, shear joints here. So this is actually a statistical analysis of the entire slope, but it's not directly found in the particular mapping cell. Okay. Okay. For the instability, the factor, we have identified about 5 of them. One is the bench face angle. Second is the geological structure. Third, joint condition, kinematic analysis, and the number of kinematic failures. And we have actually given a score system whereby whether the condition is favorable, medium, or adverse. For the adverse condition, we give 2 points. The medium condition, we give 1 point. The favorable, we give a 0 score. So, and the actual value of this is given here, bench. Like in this case, the first attribute, the bench face angle less than 50 is a 0 score. 50 to 69 is 1 score, is 1. Greater than 70 is score of 2. Geological structure, we have massive and non-persistent joints. That means the score is 0, 1 or 2 joint sets. Medium persistent joints, score is 1. Multiple sets, closely spaced and persistent joints, 2. Joint condition, we have rough, irregular, and dry, 0 score. Undulating, plain, moist, 1 score. Clay infill and silicon-sided, score is 2. Kinematic analysis, especially those you don't have deep failures, 0. The deep vector within the vertical critical crescent, 1. Deep vectors daylighting within the plus minus 30 degrees of the facing direction, we score is 2. Then we have the detected number of kinematic analysis failure. None is 0. Single failure is 1. 2 or more failures is 2. So actually what we did is that to get the instability score, we will add them all together. In this case, you can see this is what I found in the particular mapping cell. I got a score of 2, here 1, 1, 0, 0. So my total instability score is actually 2 plus 1 plus 1 plus 0 plus 0. Total is 4. This is the actual score for one particular mapping cell. So this will be later combined with the consequent score. Okay. This is how we present the mapping cells. It looks like the shape of actually the cells are built up to form the representative shape of that slope. So these are the 5 instability factors that was mentioned in the earlier slides. And these are actually, say, for example, the earlier example is taken from here, 21100. So these are being added, and eventually we will have one score. Same goes with geologic structure is here, joint structure is joint condition is here, kinematic analysis, and also number of kinematic failures. So the next slide will show you the resultant. You can see this is 4. Bench number 3 changed 60 to 80 at bench number 3. You go back to this slide, it's actually bench number 3 changed 60 to 80, 21100. Then you come to here, this is the resultant. So you have this score of 4. So the other cells are also the same thing. So you can see the score is 4 for this instability. That means this is the aggregate score from 5 instability factors. Okay, next we talk about consequence. How the consequence affect the risk. I mean, how the consequence affect the risk. So there are okay, this is the same slope that we are talking about. I show in the first slides. This is how the slope geometry can influence the impact of the rockfall. That means the consequence of a rockfall. If, for example, if a rockfall were to fall here, it drops into here, it will be safely retained by this wide berm. Okay. If a rockfall were to happen around here, the berms are so narrow. So naturally, you will end up on the road, on the highway, which is very dangerous. On top of that, you can see over here, the rock ditch, which is the rock trap at the bottom of the slope. Typically, they have a rock ditch where they can trap the rock that's between the highway and the, or maybe and the rock face. If there's enough space, maybe the rock fall that can happen, drop from even from the top or what, it can land safely without affecting the operation of the highway. So this is how the geometry of the slope can help to reduce the consequence, reduce the impact of a rockfall. The rockfall may be happening here, or it may be happening here. So all depends maybe how wide is the rock ditch, how wide is the berm here. So if you know that you can see from here, the berm is very narrow, whatever rocks that fall off will tend to bounce and drop down to the bottom. And if the bottom is also very narrow, of course the rocks will end up on the highway lah, which is going to be which will be very dangerous. Okay, this is just like a schematic lah. Okay, like what I explained earlier. If you have a number of benches here and your bench is very small, the rocks will drop, will end up here, and your expressway is almost right at the bottom of the toe of your slope, then it's going to be a dangerous situation. But on your right hand side, if I have a rock dropping off from here, and if the rock ditch is wide enough, it can safely contain and trap these fallen rocks. And what we have found is that the berm needs to be of certain dimension. So that is what is considered safe, what is considered moderate, and what is considered adverse. So we have found that there's certain ratio. The ratio of the berm with respect to the height of the bench height, B/4 less than 0.4 is considered unlikely to trap anything lah. Basically, in that project we had the typical height of the bench face is 10 meters, and the design width of the berm is 4 meters. But it is actually not always the case. But during the construction, some of them are left with 2 meters only, some are 3 meters, some are wider, 5, 6 meters, some are 8 meters, some are even 10 meters. So it's important for us to capture the as-built condition of the slope. Although the design is width of the berm is supposed to be 4 meters, but it's never been, in most cases, it's never been accurate. So we have to develop the actual, the as-built slope geometry. How we do it, we got it from the cross sections, which I mentioned earlier, which was generated by LiDAR. Next we have is, okay, this is an example of a small rockfall able to be contained within the berm. The rockfall is maybe 1 cubic meter to 1 cubic meter in size. And it so happened here, the berm is quite wide. So it's been deposited only on the berm. The highway is a few more benches down. So this is the actual small rockfall at the berm, which the berm is wide. So it doesn't affect the, what do you call, the safety of the highway user. This one is the rockfall is retained at the rock ditch. So because this rock ditch is quite wide, and this piece actually fell off and came and landed in the rock ditch. So it doesn't affect the operation of the highway. But of course, the client was very concerned, so we ended up having to repair this also. So the rock ditch is also very important. To me, the rock ditch is the most important feature in the design. Again here, there's a white berm here. It's an effective retention of the rockfall. But over here, an example, the berm itself is either very narrow or inclined. So any of these pieces, rock piece came down, it won't be trapped here. You end up down here and then maybe spill over to the highway. So this is something that is need to be assessed individually, not just the actual measurement. So although this is designed as, this berm is designed to be 4 meters, the height of the bench is 10 meters. Effectively, this is like the berm is hardly the width is very, very small, hardly anything. I think nobody can even walk on there also. So let alone a rockfall. Okay, I had the opportunity to work in the dam project about 2-3 years back. And this is actually, this dam was constructed some 40 years ago. And after they have completed the dam, this is the location of near the spillway. This area has been inaccessible. And there has been a lot of rockfalls from these slopes. So what I noticed is that the rockfall debris is limited to a certain zone only. So it was like, if the height is about 10 meters, this one is like well within 8 meters, which will give you a retention, what do you call, which gives you a good, quite relatively good retention. So I've drawn here the width of that debris field from this rockfall. Actually, very rarely you have this experience to actually find out this condition. But because this slopes here is already cut off from, is inaccessible to heavy machinery and all that. So this rockfalls has been left there for the past 40 years. So this is actually an evidence of, from the historical rockfall, how far the debris field can go. Okay, now I'll talk about consequence scoring. The consequence score relates to only factors relevant only during a rockfall event. I mean, if there's no instability, the consequence has no meaning. It's only when there is a instability, then the consequence comes into play. And moreover, if you have good consequence, it does not improve your instability, does not improve your stability of your slope. It does not influence the likelihood of instability, because consequence is, say for example, if you have a very a live highway at the bottom of your slope, then any rockfall will have consequence. But if you really stabilize your slope, then even though you have a very busy highway, the consequence is not is not what you call, not significant. But so actually, how does the consequence affect the risk of the how does it affect the risk of the rockfall imposed by the rockfall? So as mentioned earlier, the four factors are identified. There are four factors identified for the mitigation of impact by a rockfall. Firstly, the efficacy of the berms, whether the berms are wide enough or narrow. These berms are at the intermediate level, maybe from the first berm, second berm, and all the intermediate levels. At the bottom of the toe, we have the rock dish. The efficacy of the rock dish is important now, because the efficacy of the rock dish is the last line of defense for the rockfall. Then also we have to consider the height of the actual instability. If I have a instability that is likely to happen at 30 meters high, that is something to be worried about, because you never can be quite sure that how far the fellow can the rockfall will end up, whether it will land directly on whether it can be captured by your rock dish or not. But if you know it's 10-meter high, maybe your rock dish can take it. But if you talk about 30-meter, 50-meter high, you might be concerned that it may not land directly into your may not be caught by your rock dish below. Then another thing is whether the presence of any safety netting or shotcrete, things like that. So next, I'll talk about, elaborate more on the retention of berm. Okay, we have identified a certain ratio, BH factor, we call berm width over height of bench factor. Say for example, over here, BH factor is less than 0.4. That means for a 10-meter slope, the width of the berm is only 4 meters. So we are concerned that this has considered as a poor retention. But if you have a berm, say for example, if the height is 10 meter, if your berm is 4 meter to 8 meter, this can be considered as moderate retention. Well, we give a score of 1, for example, in this case. And if the BH is 0.8, say for 10 meter height of bench height, your berm width is 8 meter, this is considered good retention. So it's of low consequence, we give a score of 0. Similarly, for rock ditch, also we do the same. It's the same as the berm. For retention, you get 2, the score of 2. Moderate retention, you get score of 1. And the low consequence, that means it's good retention, you get a score of 0. Then say comes the fall height, the height of the instability of the rock mass above the expressway. We have, if it's more than 50 meter, that is very great height, we give a score of 2. 25 to 50 meter height, we give a moderate height, consider as moderate height, we give a score of 1. And less than 25 meter, we give a height of 0, low, consider as low height, score of 2. So all these 3 elements, we add them together, 1, 0, and 1. The total consequence scores become 1 plus 0 plus 1 equals to 2. So this score is actually for one particular mapping cell. Quite similarly, what was being treated, what was analyzed for the instability score. And this was the slope geometry that has been developed. You will see that all these are each mapping cells. These are all the data from each mapping cell. For example, here, you can see from here, this particular mapping cell, the height is 30 meter. That means this height is 30 meter from the expressway. The berm width, B equals to 4.0 is 4 meter. And the bench face angle is 50 meter, 50 degree. And then we have the bottom part. This one is, sorry, this is supposed to be the rock ditch. The rock ditch here is 5.0 meter, 5.5 meter. So these are all the properties that can be found at the particular mapping cell. The mapping cell in bench number 4 at chainage 180 to 200 meter. So from here, you can actually see when the H is 30 meter, based on the table earlier in the earlier slides, is between 25 to 50 meter, the consequence score is 1. The B over H ratio is 1 is to 2.5. No, sorry. The B over H ratio, one of them is H, one is 4 meter, this B over H ratio is 1.25. So it's less than 0.8, the consequence score is 0. Then followed by the rock ditch. Rock ditch actually is red below, actually, sorry. It's red below here because it's at the lowest berm. So it's 5.9 divided by 10, you get 0.59. So in this case, it's between 0.4 and 0.8. The CS score is 1. So you actually, so is this 1 plus 0 plus 1. 1 plus 0 plus 1. Okay. So the consequence scores is being aggregated from the 3 consequence factors. So in this case, it's 2. 2 is from 1 plus 0 plus 1, you get 2. The consequence score is 2. Next, okay, this is the risk, the definition of risk and with respect to consequence and probability lah. The risk is actually the product of probability and consequence. So naturally, the risk score should be instability score times consequence score. Instability is actually is the probability of failure, probability of a slope failure. Yeah. So earlier on, I have shown the instability profile. These are the two profile, one profile and consequence profile. So what I did, I want to get the risk score is just for this particular mapping cell is 4. I got 4. Here I also got 4. 4 times 4, I get 16. So this is how I get my risk score. So you can see here, say for example, here, 7 times 4, I get 28 here. Okay. So it may be, in this case, you can say it may be 7 is considered high risk here. Is adverse, 7 considered adverse. But because it's being mitigated by the consequence is only 4. So 7 times 4, you get 18. 18, you see this is yellow. Yellow is like moderate only. It's not really like as bad as it can, because over here, like 7, maybe rockfall is likely. But 4, you probably, the berm is wide. Also, they have the rock ditch there to protect the to minimize the impact. So you get about 28 here, the score. This score has to be determined by a matrix. So the matrix in the, I think it's the next one. The matrix is here. Like just now, say here 16, you'll find that 16 is somewhere here. So it's actually yellow. Yellow means moderate risk class, the risk class. So this one, the two extreme is the worst possible case is 60. The most safest case is 1. So you build up your risk matrix depending on the scores that you have, probably from your maximum score to the 0 scores, the lowest possible score. So from here, the risk matrix, as here in red, I've actually developed something like high risk is 35 to 60. So these are potentially adverse condition and all that. Then moderate is the yellow, 7 to 34. So these are moderate risk. And of course, the blue is the low consequence, low risk. Okay, maybe there's an interesting observation that we have found during the study. What is the limiting size of the unstable block? It's important to note that this type of risk categorization is actually on the bench level only, because we are not able to analyze the entire slope as yet. Because if it's the entire slope, there's a failure that affects the entire slope, then it will be treated differently already. Because this this analysis only allows for failure to happen within the single bench face by itself, not a slope failure that affects multiple berms, multiple benches. In this photograph, you will see that there are some joints that are quite prominent. Basically, these are stress relief joints. You can see here and here and here. These are joints that are developed during the unloading of the excavation, because this was previously the overburden was soil, then followed by some rock, then cutting down to here. Then these have been exposed for maybe about 40 years. This slope has been exposed for 40 years. So the stress relief joints tends to develop along here. And they are daylighting mostly. But the good thing is that they are quite irregular joints. They are not plain. These joints, when it's brand new, is not obvious. It's not there. But over the years, the past 30, 40 years, it starts to develop. And what I notice is that here to here is about 10 meters. They are only occurring at about 0.3 of the height. So this is about 3 meters maximum. You don't see any of these stress relief joint below here. You can see here, this is about 3 meter, maybe some here at a shallower depth, but maximum is about 3 meter, about 0.3 times the height of the bench face. So this is a good rule of thumb to design your rock bolts, how you will, how you can take care to stabilize this type of potential blocks. So you can see here, okay. Graphically, I've drawn this as sketch this. The slope, the berm is about 4 meter. For this particular slope is about 4 meter. The height is 10 meter. And graphically, you draw it. This is where the potential failure, the depth of that stress relief joint is here. So if you know that this size is here, you design your rock ditch to be of adequate size. So more or less, you already taking care of this possible failure. You don't have to worry about, oh, whether my rock ditch is big enough, because this is the maximum size that can chip off and drop off from your berm. So you have a buffer width of, say, about 8 meters. I think it will be quite sufficient. Yeah. And so this observation is very important. It's quite crucial to analyze, to do the spot bolting. In case you want to do a spot bolting here, you can do it beforehand, after before it start to deteriorate. The stress relief joints become bigger and bigger, then nobody will ever want to go back and do it again. Yeah. Okay, this is also another one. What's happening? This is another condition whereby the block size, if it's about 2 meter, it can be safely contained in a 4 meter berm width. If the block size is 2 meter or less. Okay, this is also the same thing. Oh, the other thing is that I would recommend a wide berm. at about 30-meter high, because the height, if the height is 50 meter, if the slope continues up like that, so it becomes more dangerous. But if you design the rock, the slope, I say at the 30-meter height, you design a wider berm, say 2 times the typical berm, then any of this failure can be easily deposited here, rather than allowing them to tumble from here to here down and all, don't know, 50 meters down or whatever. This is quite dangerous. So we actually, this berm is like a break. It's a break in the berm, make it wider so that it can catch the rock falls at mid slope. This is a mid slope. And important thing is also to have adequate rock ditch size here, because this is actually the rock ditch, the rock trap at the toe of the slope is the last line of defense. And the slope, the break in the berm is to catch those from even the upper berms. So I think this configuration will be useful to mitigate any potential rock falls from very high up in the slope. So the summary of this assessment, we have actually developed 3 graphic profiles. The profiles being stemming from the development of the concept of mapping cells. Each of them have a instability profile, we have consequence profile, we have resulting in the risk profile. So from this risk profile, we can see where are the locations that need attention, whether you need to repair them, and the areas where you don't need to worry. So the scores are given from these factors are all in similar profile. So you can easily compare between the instability and consequence profile to get the resulting profile. So extent and location of the high risk zones are identified, indicated and identified within the profile. In the profile, there is easy visualization of the risks involved. The assessment, as mentioned earlier, is for the individual bench, and it's not for multiple bench failures. And the slope profile can be presented graphically. So I think that's about it. Wait, let me see. Wow, thank you very much. That's about it. I think maybe it's a bit technical. I hope you guys are not turn sleepy or what.
No, it's okay. Sounds interesting. Something new also with your approach It's quite different from the traditional ones.
The traditional one eye see, that means they will declare whether it's safe or not safe already.
No, I think it's more than that. Okay. Anyway, now we open for discussion, Q&A session. I think we are all in Zoom. So those of you who would like to ask questions, I think it's preferred that you ask the speaker directly. Turn on your camera and then you ask directly, rather than going into chat. Yeah. So I see there are 1 or 2 questions in chat, but I actually personally I prefer you to ask direct. If you can turn on your mic, also turn on your camera. Okay. Anybody want to start the Q&A session? Want to start? Actually, I see Fateh Chan, you have a question in the chat, but if you can you just ask directly to the speaker? Fateh, are you there? Oh, Fateh Chan, are you still there? I saw a question from you in the chat. Oh, it looks like he's not around. Okay. Anybody else wants to ask a question?
Okay, I'm still here.
Okay, Ryan. Can you
Yeah,
ask
Mr.
your
Fateh.
question
No,
directly to the
I just
speaker?
wanted to find out, are the cells of the same size or they vary in size?
They are same size.
Same size,
20
that's
meter
fine
width.
then.
Yes.
Because
Yeah.
from your, when you showed a picture there, slide, it didn't look as if they were the same size. That's why I wanted to know.
Oh, no, we purposely make it 20 meters.
Okay, yeah,
So that we can just put
yeah,
it inside,
thank you.
inside the Excel sheets.
Okay, next question. We have half an hour for Q&A, so the idea is to let the audience ask a lot of questions. Two-way street rather than just listen to the speaker and that's it. I see SP Chen, you're also there, right? SP Chen, any question from you? We have another very senior guy. Chen Shipei, are you there?
Yeah.
Yeah,
Professor,
okay.
thank you very
Right,
much.
right.
It's good to see you guys. And thank you to Mr. Koay for a very interesting lecture. I think this is
It's my pleasure
really-
to share with you guys.
yes. Actually, it's something actually is outside this, directly outside the technical part of it. So we all know as a practitioner, as engineers, as geologists, we know what is good for safety. We must have rock ditch, we must have wide berm, and then we must have low slope and so on. But generally, we are not in control of what needs to be done. So a lot of this are governed by the economic part of it, the financial part of it. So in your experience, Mr. Koay, how easy or how difficult it is to persuade people who control the purse to say that this must be done, because they said, are you sure? They will ask, are you sure this is necessary? Is the risk there, or the risk is exaggerated and so on? How do you deal with it in an event like this, Mr. Koay?
Can you see the slides? Can anybody see the slides?
Yes.
Yes.
Yeah,
you look at this one. This is actually, I think, around Jalan Duta and KVE. So you see, if there's anything that drops off from here, it can end up on the highway itself, actually. So that's why that's important that the slope geometry must be adequate. The berms must be wide, and then also, like I mentioned, the last line of defense is your rock ditch. So if you don't have the rock ditch, definitely whatever rockfall will come, you'll miss. It will end up on the road now. Even a piece of rock the size of a helmet also, I think that can cause accidents. People trying to avoid that boulder, a small boulder. People can get killed and can end up hit the crash barrier, guardrails, and all that. So it's very important. I hope somebody, people from JKR can have attend this. They can take this cue that, for example, in the JKR slope guideline, they did not touch on rock slopes, but they only touch on soil slopes, and they give a general blanket, what they call approval on guideline for soil slopes. The berms can be minimum 2 meter wide. The height of the bench cannot be more than 6 meters, things like that. It cannot be the height of the slope not more than 6 berms, But I think if JKL can expand this to rock slopes, this will be quite helpful. but provided they must get in consultation with geologists who are experienced facing with this type of problem and all that. Because I noticed these slopes was relatively quite well engineered but because the dimension of it, the berms sometimes are during construction it just disappear, chip off and things like that. They are so though the defensive mechanism of it is not there. So when we do the slope assessment, we have to assess the actual slope condition. We physically go back and measure the slope geometry. In this case, for that project we have LiDAR. We have LiDAR. We have cross sections. The slope geometry attributes are all obtained from the cross sections. So width of berm, the height of berm, height of the bench, all are recorded obtained from LiDAR.
Yeah, just a comment. I think JKR, most of their works are done by geotechnical engineers who are mostly soil mechanics people. So that's why less of rock mechanics. Rock mechanics more by engineering geologists, maybe mining engineers. But some geotech engineers also do rock slopes, but that's a minority. I think most of the traditional JKR civil engineering, geotech engineers, they deal more with slopes, which is actually good for people like you, engineering geologists, because then they will need your help in doing the assessment for rock slopes. Okay, any more questions? I will call on the audience to ask questions because our audience traditionally they're very quiet. So I will have to poke them a bit. So how about Dr. Halim? Dr. Halim, you're still there? Dr. Halim is a soil mechanics man. Dr. Halim, keeping quiet or going away already? Dr. Halim, are you still there? Hi. Yeah, Dr. Halim.
Hello.
Yeah, okay. Any
Yeah.
question? Any question from you? Yeah.
Question.
Yes.
I think this one like this. Apa ni refer the outcrop there? Is it any dipping parallel to the faulting zone?
Dipping parallel to the slope face. Like daylighting and all that.
Yeah.
So I'm presenting just the basic technique only. So whether it's dipping or daylighting, it will be shown in my analysis cell by cell. That means each mapping cell will be shown. So I'm not showing any particular because these photos are taken from various sites actually. It's not just one single project. It's I think 3 or 4 projects, rock slope projects.
Also project.
This one I think the one this photo is actually NKVE. The other one is in you see the big slope is Jelapang Cangkatjering Highway, up the north of Menara Tunnel.
Okay.
So these are today because I did not give the presentation on the actual findings because I'm just presenting the techniques only so that you share the ideas how it's been carried out and it's not saying that oh this particular slope is bad or whatever. No, just the technique.
Okay. That means you just study the zero net plotting.
Yeah. We have studied the kinematic analysis each and every one. Say for example here.
Okay.
Some of these we did study, say P20, we did study in our kinematic analysis. So we have one single kinematic analysis for P20, P25, P9. We also study each of them. So the joints all from here will be put in as a kinematic analysis. So we know the stability, how how this P25 block fare with respect to kinematic analysis, or P20 or what. So each of them, say for example, P9 is here, this block. So we did study this, whether it's okay or not, whether got plane failure or not, daylighting joint or wedge or what. So each and every one is presented. Within that, the 20-meter width mapping cell.
That means the faulting method is the faulting lah, not the sliding lah.
The faulting.
Maksud the topping material is sliding or toppling.
Toppling, no. Toppling we can figure out lah, but toppling you need a quite a steep angle lah for toppling to occur lah. But in this case, we don't have a major issue on toppling lah. Only maybe plane failure, daylighting, and also wedge failure. This will be found out. Will be determined by the stereo plots, the kinematic analysis.
Okay, this is my question lah. Okay.
Yeah. Okay. Thank you.
Next question. How about Philip Tiong, our ex-student, now with GUI and partners. Philip, any question from you? Philip Tiong.
Dr. Tan.
Yeah. Louder, please.
I
Louder,
don't have
please.
much question now.
Yeah.
Yeah. Maybe just now I saw the grid line. I think in concept of mapping cell, the 20-meter width one.
Yeah.
Okay, yeah, regarding this.
Yeah.
Okay. Maybe just now I also can listen to details. Regarding this photo you show, basically you are presenting, you are suggesting when the mapping is we do in the grid line, is it?
Yes. In the cell by cell.
Cell by cell. So the benefit is maybe can be more focused on the localized which area.
Yes.
Critical
It's
area.
yes, localized bench by bench only.
Okay.
But separately, if there's a big fall or what cutting across and all, that will be separate because the big falls, maybe daylighting joints or whatever, big wedge failure coming out from the sun. This type of analysis is not suitable. It will be seen globally. That will be analyzed globally lah. So we do some of the stereo plot analysis to determine whether in that particular slope, whether we have what we call major joints sets that can cause problem to the entire slope or not. But after that one is being found not to be there, then only we start working on this procedure. So this procedure only define where exactly to repair, where to protect, where to stabilize.
Okay. I think it's a good suggestion now. Okay.
Yeah.
So I think that's all. Thank you, Mr. Koay. Thank you.
Yeah. Welcome, Philip.
Yeah, thanks.
Yeah. Okay. Next question. You can volunteer to ask question. Don't have to wait for me to call you. We still have some time, so
Maybe I can share my paper, which I did in 2019. I'll drop it in the chat box. See whether people can pick it up or not.
okay. Just write down the chat box. Yeah. Okay. How about my good friend, Mr. Robin Liao? You're there, right, Mr. Robin Liao?
Yes, I'm here, Mr. Tan.
Okay, right. I'm reserving you for the last questioner. Any
I don't
questions
know,
from you?
Mr. Tan, this is not much geology. So
Not much geology.
not much question.
Not much question. Okay.
But
Yeah,
wait,
this
Mr.
is-
Koay,
yeah.
Mr. Koay,
Yeah.
the the road cut at Jalan Duta,
Yes.
is it granite? Is it?
Yeah, granite.
It is granite. Okay.
Yeah.
So essentially,
Sorry, sir. Sorry.
as what
Sorry, are you there?
Mr. Koay,
Yeah, sorry. Yeah.
essentially, what you have said in the mitigating measures, what you have to do is to minimize the risk and to increase the stability.
Yes.
Is to have a wide berm, and then a deep, a properly designed rock ditch, and also net. Essentially, that is the conclusion you can make. Is that right?
Yeah, we are asked by the client to categorize the rock slope in terms of safety in stability So we are asked to carry out whether it's low risk, moderate risk, and high risk So basically,
so this road cut at Jalan Duta, is it high risk, low risk, or medium risk?
that slopes there are relatively low moderate moderate
Okay.
They're moderate risk
And I also noticed at this Jalan Duta, there is no vegetation cover. On the other slide, I see there are grasses and vegetation growing on the rock slope. What are those vegetation for? Is it for increasing stability or for aesthetic purposes?
Sorry, wait. Well, sorry, come again. Aesthetic purposes, stability or what?
Yeah, the vegetation cover. In this one.
This one?
This one, there's no cover. There's no vegetation.
No, actually, this one is actually there was a lot of vegetation. So happened the client go and clean it up. I took a photo of it during the time. Now it's back to fully covered already.
I see.
This was happening when I did a study. It was actually even a lot of vegetation, even got trees wedging into the joints, during that time. Then they go and clear it up. So when I was passing by, I took this photo.
Yeah, it's for aesthetic purposes. Okay. Thank you.
Okay. Any more questions? If not, I will ask a couple of quick questions. Koay. Number one, in your stereonet analysis, you use phi equal 35 degrees.
Yes.
Is that just picked from the book or something?
I think 35 is quite just a figure which is reasonable.
From the book published
from the published book and all that but
for
actual
granite slope
for in
granite
real
slope.
case in real case I think we can go about 40
Okay.
The angle of repose is about 40.
Yeah, because if it's your rock slope are kind of fresh rock, grade 1, grade 2 type, so phi can be higher 40 degrees, I think.
Yes.
Okay, that's a small matter. The other thing is in your scores, for example, in your stability scores, what is the cutoff value? You have like 0 to 10, isn't it? You got 0 to 10.
So
What is the cutoff? The danger value? Is that 5 or 6? Or?
No.
Is there a danger cutoff value like you say?
Like this one. Sorry.
Yeah. For example, the very first one. In fact, in all the three you didn't mention what's the. Normally, there's a cutoff. Okay, above that is not stable.
This one you have to assign one. This score is assigned.
I mean,
so for example, we use say for example this bench face less than 50, then 50 to 69, then 70 or more. So we assign a score of 0, 1, and
Yes.
2.
Yeah.
So the scores are actually reflective of favorable, medium, and adverse condition. So we have 5 of these parameters inside. So we just add them together. But if you want the adverse one, probably the worst one is 2, 2, 2, 2, and 2, which is how many? 10 already.
Yeah. I mean your score is from 0 to 10 lah. So where's the cutoff? Total score for each cell. What is the cutoff? Is that 5 or 6 is not stable, for example? You didn't actually mention. Yeah.
Yeah, but it's we did not mention the total score
for each cell. So if it's 3, of course it's stable. Like if it's 6 is not stable, for example. Yeah.
Okay, like for example, I did it over here. You can see the consequence score. This is low consequence.
Yeah.
3 to 4, 5 to 6. These are just arbitrarily I put it in to separate out because I know the worst possible score is 6 in this
6
case.
lah, yeah.
6
So that
so I
5
put
or
5 and
6
6 is
5, 6 is bad
the
lah,
worst case.
Yeah.
Then moderate is 3 to 4, and then low consequence is 0, 1, and 2 lah.
Right.
Same goes with this one.
Okay. Yeah.
The instability one, I did not put, but I think this is about adverse is about maybe 8, 9, 10 lah.
Yeah.
Then 4, 5, 6 is medium lah. Then 0, 1, 2, 3 is favorable lah.
Okay.
But the main thing,
My other question is this: you're doing based on bench slope lah, but in general for practical slope stability, rock slope, we actually look at the overall the big slope lah, the whole slope.
Yes.
We avoid it when a major part of the slope fail lah, not the bench slope. If you got 1 or 2 bench slope failures, it is not considered a risky thing. You know, it's only when there's a major slope failure, either by wedge failure or plane failure, cutting through several benches. And that's the major problem. Okay, yeah.
So that's why my title is actually engineered slope, engineered rock slope. That means it has a certain more or less dimension, geometry, but we actually study the real as-built condition of the slope actually, because the engineering maybe they wanted to have 4-meter berm, but in actual fact is 2 meters. Some are wider, some are smaller than that. Then the height of the benches also 10 meters, some are 9.8, some are 10.5. So that one, the height of berm, the benches is quite consistent relatively but the width of the berm are not. So
okay, my one last question. I'm curious. I saw through your CV. Sometimes you work in the capacity of a geotech engineer, not just engineering geologist. Is that really possible?
In a way,
yeah.
To be honest, some of my real appointments are engineer.
Geotech engineer not as engineering geologist.
Not as engineer, because in fact it started as way back as 1992.
Yeah.
My position at Renhill was geotech engineer. That was way back lah.
Yeah.
Nowadays people are more particular about that, whether you are geologist, you're not engineer and all that. But I can tell you that I'm quite well experienced in terms of the engineering, geotech engineer, even structural engineer. Because when I first started working in Renhill, my position is such not because of anything else.
Okay, yeah. Okay, anybody has a last question before I close the session, the talk? We still have 5 minutes. If anybody has a last,
I don't know how to attach my file actually.
attach which file?
I want to attach my
Publication.
my paper publication.
Oh, no, you just list down the title is good enough. You-
Mr. Tan, there is a question in the meeting chat.
Oh, chat box.
Yeah.
Who is asking? You can ask directly if you want.
Ikram Jamil.
You can ask directly. Who is this is retaining wall. Chat box. Sorry, sir. I would like to, okay, say sorry, sir. I would like to ask for an opinion or any thoughts. Do you know about anything GCCM, geosynthetic concrete canvas? It is suitable for igneous rock or other rock. Right, you're sharing your thought based on your experience. Koay, you want to answer that? This is a retaining wall at slope surface cover.
Not that I know
Uh,
of, actually. GCC,
GCCM, geosynthetic concrete canvas.
not that I know of.
Your,
And then
your
I'm
answer,
sorry,
comment?
I've not heard of it.
No, okay, answer is no. Okay,
Those who are interested in my paper, maybe you can text me. My phone number is there. Just text me. I can give you all the copy.
okay. Otherwise, you can also ask through me. I can always ask Koay, and then I will send a reference. Okay.
Reference,
Nope.
I think I cannot find it myself, actually.
You can't find a reference. Okay.
I cannot find it in the net, actually.
Okay. Robin, any last question before I close?
No, sir. Thank you for organizing
Okay.
the event.
Right. Okay. Then in that case, can all of you turn on your camera so we take a photo, take a group photo for the Warta Geology before I close the session.
Photo.
Okay, please turn on your camera, and I ask